Welcome to Chapter 5, Section 2, the definite integral. In this video, we're going to be using some slides that were provided to go along with Stewart's Calculus Early Transcendentals 8th edition. Very grateful to have those. And as I usually do, I'm going to go through and make some comments on these slides. Some of them I will comment on, some of them I won't. Some of them I will draw some additional diagrams and make some notes, and I'll highlight some things that I think that you should pay special attention to. And then when we get to the end of this group of slides, and there are a bunch of them, but we're not going to look at all of them in detail, I will switch over and work through, or at least talk about, some problems from a homework assignment that I'm going to be giving to my students. So let's start off by, this is going to be kind of informal sometimes because there were like 48 slides or something. So I don't remember exactly which ones I'm going to look at. I did put some check marks on some ones that I know I want to pay special attention to. So let's just sort of chat our way through these slides. This we've seen previously, and actually this notation from the previous section was something that I thought was a little bit curious because I don't think it's extremely typical, at least not in my experience, but it's been a little while since I sat in a Calc 1 classroom. X sub 1 with the asterisks on it was indicating that there is an x coordinate that we're using that's somewhere in the subinterval of the strip or the rectangle that we're going to be finding the area of as we go through and add together all the areas in order to find, in this case, since we're taking the limit as n goes to infinity, the exact area under the curve, or if it were for a specific n value, an approximation for the area under the curve. So we are familiar with this notation. This is the area of one rectangle. This is the area of the second rectangle. And if this had been an x sub 0 without the asterisks, it would be a left approximation because we would be using the x coordinate that is on the left-hand side of the rectangle in order to calculate the height of the rectangle. Leading with an x sub 1 in this first terms means that we're finding a right approximation. And in this case, x sub 1 star is somewhere between x sub 0 and x sub 1, somewhere in that first rectangle. The definite integral. Excuse me. So f is a function. It needs to be integrable, which we encounter later in this slide. We're still working on some kind of a defined interval. This is a closed interval because of the or equal to symbols here. So we're finding the area under the curve, so to speak, from A to B. We like to take that interval and divide it into n subintervals of equal width. And we've seen this calculation of delta x previously, b minus a, divided by total number of subintervals that we'd like to work with. X sub 0 represents the leftmost x coordinate on the interval, so that would be your a value, and the nth x value would be the last available value on the interval, so that's b. That would be the right-hand x coordinate of the rightmost rectangle or strip. Okay, and those starred x values represent sample points, and sometimes those are what we're going to be using as x values in order to plug into our function to calculate the height of each rectangle. The definite integral of f from a to b is represented using this notation, and on the next slide we see that we get to talk in a little bit more detail about it on the next slide. This symbol was introduced by Leibniz, a very famous mathematician, It's called the integral sign or integral symbol. It's an elongated S because it's a limit of our sums. So we're summing, we're adding together all the areas of those rectangles. Very often, this part of the expression or the integral I refer to as the argument. More formally, it is referred to as the integrand. And A and B are the limits of integration. You've got a lower limit and an upper limit. And typically, I'll say, at the moment anyway, the number that's at the bottom here, which is represented by A, is going to be less than B. Don't worry about dx, except for the fact that it means that we're taking the integral with respect to x. It means that x is our independent variable, like y equals 3x minus 4. X is the independent variable, y is the dependent variable. So pulling out some vocab from a little ways back, probably, the procedure of calculating an integral is called integration. And the variable that we're working with doesn't really matter. All three of those integrals are equal to each other. And the sum, this sum right here, where we're adding up the areas of all of those rectangles that have a height of f of x sub I and a width of delta x, which is b minus a divided by n. That sum is called a Riemann sum. And I mentioned Riemann in the 5.1 video, and I couldn't remember his name, and it's Bernard. My apologies, Bernard. Died when he was 40. Just imagine the contributions that he made to mathematics before passing away at 40. If he had lived to be 60, the world might be a different place. All right, so thanks, Riemann. And in definition number 2, we can adjust the degree of accuracy of our Riemann sum by making the rectangle skinnier, or by choosing different x sub I star values or x sub I asterisk values. And if we make the rectangles really skinny, we end up finding the exact area. So there's the shading underneath a portion of an arbitrary curve. So again, the integral from a to b of f of x with respect to x can be interpreted as the area under the curve. Which curve? This curve, y, which is some function of x. From where to where? From a to b. This is going to happen, and for those of you who are going farther than your study of Calc 1, you'll definitely see this, and if you move into Calc 3, this becomes a real challenge. But it is possible that you're going to need to find the, so to speak, area under the curve for a curve that dips below the x-axis, and you should be made aware right away that calculating the integral just on this interval from here to here would return a positive area, but from here to here it would return a negative area. And why is that? Because the area of each one of these sort of tan colored rectangles is found by taking the width of the rectangle, dx, or delta x, and multiplying it by the height. And the height is the y coordinate, either the y coordinate at this point, or maybe the y coordinate at the midpoint, or the y coordinate at the right side, or right end of that interval. So delta x times this y value, that's definitely going to be a negative y coordinate, so it's going to show up as a negative area. Sometimes that's okay. Sometimes it's valuable. If you're calculating total income, total revenue, something like that, total amount of weight gain by a person. Well, if they lost weight, I want my weight gain to show up as a negative value for sure. So sometimes that's valuable. But if we're looking for a total fluctuation, a total distance traveled, I don't care if I when I leave and I go to work, if it's 20 miles to get to work, and then I'm traveling a negative distance in order to get back to my house, it's not 0 miles. It's not 20 plus negative 20. It's definitely 40. So we would maybe need to take the absolute value of that negative region. So sometimes we're happy to have it be negative, and it increases the accuracy of maybe a word problem, and sometimes not so much. You don't want it to show up as negative. So you would have to cut your interval up into, in this case, 1, 2, 3 regions. 1, 2, 3 regions. A definite integral can be interpreted as a net area. So in this case, if we just evaluate the integral from a to b, this tan colored region down here will get automatically interpreted as a negative area because of what I was saying earlier about the rectangles having a negative height because of the negative y coordinates at what turns out to be the bottom of those rectangles. You're welcome to read this. I don't think it's going to be very beneficial to you right now. All it's saying is that it almost doesn't matter the width of the rectangles. If we don't chop up the rectangles into regions that have equal widths, it's going to be okay as long as the largest width, it's saying here, as long as the largest width with a maximum value of delta x sub I approaches 0. So as long as we're still taking a limit down here that causes our rectangles to become extremely skinny or narrow or not very wide, then it's okay. We'll still get a solid value for the area under our curve. We will still be able to evaluate the integral using a Riemann sum, where we're applying a limit to the Riemann sum. This is, excuse me, very general and very specific at the same time. Normally we're going to be working with continuous functions, or maybe there will be one point of discontinuity. Maybe there's going to be an asymptote on the interval that we're working with. What Theorem 3 is saying is that if our function is continuous on the closed interval from a to b, or if the function has a finite number of jump discontinuities, then we can still integrate. F is still integrable. We can still find the area under the curve. All right, here it is. The integral still exists. That's, of course, not the scenario that we're going to start with. We don't want to start with finding the area under a curve that has some arbitrary number of finite jump discontinuities. That's just mean. All right, what are we seeing here in this slide? Still about the definite integral. To simplify the calculation, we don't see a single point. Right. So usually what it's saying here is that we use right endpoints in order to calculate the height of our rectangles. Yep, there it is. Starting out with x sub I, where your index is starting at a positive 1. So we're not starting out using x sub 0 to calculate the height of our rectangle. We are using x sub 1. And that's pretty typical. And then here are the little calculations that we can do to find delta x and to find our specific x sub I values. We're starting out at the lower end of our interval that goes from a to b, and we're adding I widths, rectangle widths, where each rectangle width is delta x. So we can march our way out to the appropriate rectangle. All right, finally, an actual example problem. This one has us expressing this limit as an integral. And we are going to be applying a limit to our Riemann sum. So we're going to have infinitely many rectangles. So we're going to find a super accurate, if not precise, value for the area under this very unusual curve. And we're integrating from 0 to pi. So a is going to be our lower limit of 0, and we're integrating up to pi, so that'll be our b value. And the function that you see inside the summation notation up there is x to the third plus x sine x. And so the statement at the top of the screen, the limit of the Riemann sum, can be expressed as the integral from 0 to pi. And this number 1, I'm quite sure, is supposed to be a plus sign. Yep, so the integral from 0 to pi of x to the third plus x sine x with respect to x. So this would be the answer to the question, expressing it as a definite integral. You can read that, that's nice. And then we're into evaluating integrals. Something that will be helpful in the process of evaluating integrals will be to have a familiarity with these sums. There are proofs for these, but they're just being given to you here as raw materials. If I were you, I would pause and jot these down. We're going to use these, and my guess is whether you're one of my students or somebody else's students, you're going to be using these in a homework problem. And in fact, I don't have them memorized, so I might have to come flipping back here in order to grab those, to utilize those. And then these, you have probably seen these before. Here in number 8, hold still. In number 8, we're adding up a bunch of constant values. When I is equal to 1, this constant value is c. When I is equal to 2, the constant value is c. So how many c's are we going to have? As we go from 1 to n, we're going to have n of them. So we end up with just n times c. Number 9 shows us the property where if we have a constant value, c, that's multiplying times our a sub I, and this is some series of terms, right, the ith term. If each one of the terms as part of our sum has a constant multiple, we can factor that constant value out in front of our integral, or our sum rather. We can do all of the addition here, get an answer, and then multiply by our c value. Number 10 is basically the distributive property of summation. 11 is the distributive property of summation over subtraction. And let's look at example 2. Evaluate the Riemann sum for this function, taking the sample points to be right endpoints. Sample points being right endpoints, we need that information. And your limits of integration, so to speak, are going to be from 0 to 3. And we're going to take that interval and cut it into 6 pieces. And then we'll go in and evaluate it using the actual integral. So for part A, with n equaling 6, we can find delta x by doing b minus a divided by n. That's 3 minus 0 over 6, which reduces to a half. Therefore, the right endpoints are, and I'll point out that x sub 0, which we're not using, that would be a left endpoint, is equal to 0, because that's our a value, right? Our interval is going from 0 to 3, so x sub 0 is our very first x coordinate, which is the a value, which just so happens to be a 0 in this case. And then our right endpoints step forward by 1/2 over and over again, so x sub 1 is 0.5, x sub 2 is 1.0, and so on, all the way up to x sub 6, which is 3.0. Our Riemann sum is found by taking the height of each rectangle as determined by taking the right x coordinate of each rectangle, plugging it into the function, generating a corresponding y value. So that's the height of the rectangle Delta x, of course, is the width of the rectangle, and delta x is consistent all the way across. In this summation, it's 0.5 or 1/2 over and over and over again, and you can see those 1/2s right here and here and here and here and here and here. In all 6 terms, we have that multiple of 1/2, so it's been factored out. And then in the parentheses, we are adding together all of the y values that were generated by f of 0.5, f of 1.0, f of 1.5, and so on. We do all that arithmetic, then we multiply it by 1/2, and we get a negative number. We got a negative number because if we look at the graph, these are the rectangles for which we added the areas together. And the first 4 rectangles, because they were defined by their right endpoints, our first rectangle had a negative height, second rectangle, negative height, third one, negative, fourth one, negative. Multiplied by the width of 0.5, those turned out to be 4 negative numbers. Only these ended up being positive, and those circles were kind of weird. This one has a positive height, and x sub 6 used an x coordinate of 3 plugged into the function, gave us a positive y value, so that last rectangle has a positive area. We added them all together, and it turned out that the negatives outweighed the positives, still giving us a negative sum. In part B, with n subintervals, right, so in part B, we're still working with n subintervals. We're still taking from 0 to 3, b minus a, still equal to 3. We're cutting that into n pieces, and this is not very well articulated here, but the general version of the statement is here. Each one of our x sub I values can be generated using this little formula over here, x sub I equals 3i divided by n. And that was derived maybe by looking at this pattern right here. That's one way to say that. So x sub 0 is 0. We know that that's our a value. X sub 1 is 1 delta x to the right of 0. Delta x, as we see up here, is 3 divided by n. So what's 0 plus a? 3 over n? It's 3 over n. In order to go from x sub 0 to x sub 2, we would have to add 2 delta x's. And what is 2 times delta x? How about 6 over n? And 3 delta x's makes 9 over n. So generally speaking, x sub I is equal to, it's 3i over n. You can see that. I would also say that it's equal to I, 3 over n's, because we're really doing I times that as our delta x value. All right, so that's more detail than we needed. Maybe, since we're using right endpoints, we can use theorem 4, which says that this integral is equal to the limit. Is very important, right? Because when we're performing an integral like this, n needs to go to infinity so that we have a hyper-accurate answer, in fact, a precise answer. We're still taking the height of our rectangles, multiplying them by the width of our rectangles. The height of the rectangle is found by taking the right endpoint, x sub 1, x sub 2, x sub 3, right? Those are x coordinates, plugging them into our function. So f of 3i over n, that's coming from right here. And then multiplying that resulting y value by the width of each rectangle, 3 over n, delta x. So it is still infinitely many rectangles with a height of f of 3i over n times the width, the delta x value, 3 over n. We know what f of 3i over n is. I can't draw across pages, but what's a good way to do that? F of 3i over n, up there near the top of the page, I've highlighted it in blue. If you take 3i over n and you plug it into this original expression or function, f of x, which is x cubed minus 6x, you get this expression on the next slide. So you notice the 3i over n's. What happened to the green 3 over n that I highlighted up here? Delta x. Well, n is a constant value, and 3 is a constant value. So we can factor that constant value out of the sum. We still have to leave it inside the limit, but we can factor it outside the sum. So on this next slide, for example 2, notice the 3 over n right here. It's been factored out of the sum, but has not been factored out of the limit. Okay. Now we need to start doing some addition. That erased weird. The 3i over n being cubed results in the 27 over n to the third, I to the third, right? So we're cubing everything. And in this term, we're simply distributing. The 6 gets multiplied into the numerator. Nothing else has changed. Then, on our way to the next line, a number of things happen. For one, let's get in there. For one, this 27n to the third is a constant value. Remember that n is a constant value. It's an exceptionally large constant value, but it's still a constant. So that entire fraction is a constant, and it can be factored outside the summation notation. So we're essentially taking this and multiplying it by the 3 over n. So 3 times 27 gives us 81. N times n to the third gives us n to the fourth. This sigma that's right here is affiliated with this term. The sigma can also be distributed out to this term. And if it is, then this 18 over n, which is a constant value, can be factored out and multiplied by this 3 over n. And 18 times 3 is 54, and n times n in the denominator makes n squared. And this minus sign is this minus sign. So we're distributing the sigma notation, and we're doing factoring twice, which ends up giving us... I wish I could make the diameter of my eraser bigger, but I can't, so whistle while you wait. Ends up giving us this statement here. Now, we need to know a trick. We need to know how to add up the sum of cubes from 1 to n. Many slides ago, there was a slide that had 3 different little formulas on it, and I recommended to you that you write those down, and in fact that I don't have them memorized, so I might have to glance back at them. Thankfully, in these slides that were provided to us, I don't have to glance back because it's right here. The sum of cubes from 1 to n equals n times n plus 1 over 2 quantity squared. So I should not have only bracketed that inside part. It's really, let me just circle it so that we're sure. It includes that square. And the sum of all of the integers from 1 to n can be represented as n times n plus 1 over 2 not squared. Interesting. The cubed one is squared, and the first degree one is not squared at all. And then you see the 81 over n to the 4 and the 54 over n squared, and the minus sign is still there. Okay, what has happened in order to get us to the next line that's on the next slide? There has been some large-scale simplification that happened there. The n to the 4th power down here has interacted with this numerator, and the 2 in the denominator has gotten squared, resulting in a 4. The 2 from the denominator on the previous slide over here has interacted with the 54, giving us the 27 on the next slide. And so many colors. This n squared ends up interacting with this n, so you get some division by n, and then that n that was remaining in the denominator got distributed into these other two terms, the n and the plus 1. You might want to take the time to work all of that out and see if you can get it to equal. Not so much that as see if you can get all of the arithmetic to equal this. Because you're going to have to do that on your own in homework problems. So here you know that it should simplify down to this statement. So you should practice that and see if you can get it there. Then, in going from this line to this line, the limit got applied. As n goes to infinity, 1 over n turns into a 0. So now you've got 1 squared, which is 1, leaving you just with the 81 over 4, and there it is. Over here, the 1 over n also goes to 0, so you've got minus 27 times 1, which is negative 27. There it is. Common denominator, do the arithmetic, and you get negative 27 fourths, or negative 6.75. And that's your answer. What was our answer when we did it as a Riemann sum? Excuse me, it was so long ago. What was the answer to part A? Negative 3.9375. So just short of negative 4. And this one is just short of negative 7. So using the Riemann technique, we probably should have been cutting that up into more rectangles. 6 rectangles was already a decent amount of work. So 12 rectangles, 20 rectangles, that's a lot of arithmetic. Nice to be able to do it this way, but we definitely have to still know some algebra and how to apply our limits, and also knowing those formulas for the sum of integers, sum of squares of integers, sum of cubes of integers. Definitely came in handy. So here's the graphical representation. Sorry, my throat's a little scratchy. And the integral is what's giving us the exact area of negative 6.75. Yeah, you don't want to find the area of all those rectangles, do you? For n equals 40. But even at n equals 40, look, we're still off by, that's negative 6.4, let's say. And the actual area was negative 6.75, so you're still off by 0.35, even at 40 rectangles. At 5,000 rectangles, you're pretty close. If you were rounding to the hundredths place, at 5,000 rectangles, you'd get the correct answer. You'll also be dead by the time you add up the area of all those rectangles. The midpoint rule suggests that a right approximation. So starting out using x sub 1 is maybe not the best way to go. If you really want to get an approximation to the integral, you shouldn't be doing it with a left or right approximation. You should you might want to consider using the midpoint approximation. And the midpoint is going to be denoted by x bar sub I. I can't scroll there. What am I doing? I need to scroll down here. There we go. I want to be up here though. So the midpoint rule, look, all of this, it looks the same, right? This statement looks the same. We're still finding the integral with respect to x. The squiggly equal sign means that it's approximately equal to. It's still the sum of, right? It's still the sum of a bunch of heights multiplied by a bunch of widths, except the heights are being calculated by taking the midpoint of each strip, or the midpoint of each subinterval, and it's that x coordinate that's being plugged into the function to generate the height of the rectangle. And then we factored out the delta x, and we'll multiply that once we do all of the addition for the heights of those rectangles. Delta x is still equal to b minus a divided by n. And there's a little formula for calculating each of the individual midpoints for your subintervals. So in example number 5, we'll take a quick look at using the midpoint rule with an n value of 5 to approximate the area under the curve of the function 1 over x, as our limits of integration go from 1 to 2. The endpoints of the 5 subintervals are 5 subintervals. Quick, how many numbers are we about to see? No, it's not 5, it's 6. Because the first rectangle, even if there was only one rectangle, you'd still have to have 2 numbers, a left limit and a right limit. And if you had 2 subintervals, you'd need to have 3 values, a left one, a right one, and a middle one. That was weird looking. Anyway, 5 subintervals means we're going to have these 6 numbers. The first one, which is your a value, is x sub 0. The midpoint of your first subinterval is 1.1. There it is. And the midpoint of your second subinterval is 1.3. There it is. And so on. So we get these 5 midpoints for our 5 subintervals. The width of each interval is still calculated to be delta x, which is still b minus a divided by n, and subintervals. So 2 minus 1 over 5 gives us the 1/5. And the midpoint rule says that the area under the curve is approximately equal to the width of each rectangle multiplied by the height of each rectangle, where the height of each rectangle is determined by taking the midpoint of the subinterval and plugging it into your function. If we plug in those midpoints, we get these as heights. We add up the heights, we multiply by delta x, and we get this as an approximate area under the curve. And there's the graphical representation of what it was that we were just doing. Notice that at an x coordinate of 1.1, we've plugged that into our function, y equals 1 over x, and we've gotten this point, and that point has a y coordinate, which becomes the height of that rectangle. And you can see it's really nice. Look, here's part of the over approximation, and here's part of the under approximation. By using a midpoint, those two are getting pretty close to canceling each other out, and it ends up being a better approximation of our area under the curve. It sort of splits the difference between the over and under approximations that we get from using either right endpoint or left endpoint approximations. Definite integrals have some properties that are not going to surprise you, but this one I think is worth noting. You should realize that if you switch the a and the b values, if you swap your limits of integration, the result will be the opposite area under the curve. Notice what's changed. Here's the from b to a, from a to b. And if you swap them, you're going to get the opposite of what you would have gotten otherwise as your area under the curve. If your limits of integration, a and b values, if your a and b values, there they are equal to each other, then delta x, which equals b minus a divided by n, is going to equal b minus b divided by n, right? Because a and b are equal to each other. So if a and b are equal to each other, then you've got 0 divided by n, which means your delta x value is 0. So you can take all the heights of your rectangles you want, but as you multiply them by a width of 0, you're going to end up with 0 plus 0 plus 0 plus 0. Guess what all those add up to be? You got it, 0. Strange to think that that would ever come in handy, but this is math. We want to be as thorough as possible with our definitions, so that we are prepared for any eventuality. Properties of integrals. So if we're integrating from a to b, I'm looking at number 1 here. If we're integrating from a to b, and what we're integrating is a constant function, for example, what if I'm working with y equals 2? Then that would be a line that looks like this. And if I'm integrating from 1, 2, 3, 4, 5, 6, from 1 to 6, I think it would be very easy to find the area under that curve. From 1 to 6, it's a rectangle. How wide is the rectangle? Well, it's 5, of course. How'd you get that? Well, it's 6 minus 1. And how tall is it? Well, if the blue line that I drew is actually y equals 2, then it has a height of 2. So we've got 2 times 5. Well, this 2 was my c value, and 5 is b minus a. So there is your 2 times 6 minus 1, or your 2 times 5, giving you an exact area under the curve of 5, of 10. It can multiply, I promise. All right, number 2 says that there's basically a distributive property of integration over addition. Number 3 says that we can factor out that constant value again. Notice the c, it's going from inside the integral to outside the integral. Remember, these integrals are limits of Riemann sums. So the rules that apply to the Riemann sums with the sigma notation, those rules are applying here also. Number 4 is the distributive property over subtraction. This is the diagram that basically I just drew for you. Of course, that's a lot prettier. Not as many colors though, so take that. And then I think the rest of these slides are more detailed explanations of those properties that we were just seeing a couple slides ago. Yeah, 2 slides ago. Property 2 says, in general, property 2 follows from theorem 4. So a little bit of a proof there. Notice that this integration, that works. Notice that this integration that you're seeing over there immediately turns into the limit of a Riemann sum. So I was saying that the rules for the sums and the rules for the integrals end up being pretty much the same in terms of the distributive property and factoring out a constant value. Property 3 is very similar. There is no such thing as subtraction anyway. Subtraction is really adding a negative number. So that works out. Use the properties of integrals to evaluate this. This integral is being distributed to these 2 terms. It's going to the 4, it's going to the 3x squared. So that's how we arrive here. And then the 3 that's in the second integral is being factored out and placed in front of the integral sign, leaving us with this expression. And now we get to apply some properties that we were just talking about. Notice that in this integral, you're integrating from 0 to 1, and what's your integrand? It's a constant value. It's the number 4. So you can use this property in order to evaluate that integral. And here, this is a bit of a throwback. We're integrating x squared from 0 to 1, and on the next slide we're reminded that in the past, previous section, we evaluated this and it turned out to be 1/3. Okay, that was another problem where we looked at a table of values and we took our n value, where we were creating the number of subintervals or the number of strips, and we took n and we made it bigger and bigger and bigger, and we were looking at right approximations and left approximations, and it turned out that those approximations squeezed us in to the point where the value of 1/3 was clearly the direction we were heading with that integral from 0 to 1. So utilizing that, we can replace the integral from 0 to 1 of x squared with respect to x. We can replace that with a 1/3, and then all you have from there is arithmetic for a final answer of 5. You can go back through that more slowly. We have another property that says, I forget if there's a graphic that goes with this one. Yeah, there is. So notice here we're integrating from a to c, and then from here we're integrating from c to b. So we're going from a to c, and then from c to b. And I drew that from left to right because that's what we're doing. These are numbers on the x-axis. And so where are we really going? We're really going from a to b, which is why this is equal to this last integral, which says that we're just integrating from a to b, from very beginning to very end. Why would I do that? Why would I take two separate integrals that are actually like adjacent to each other? Why would I take this one and this one? Why would I have them separately to begin with? I don't think you would. You might, but maybe not. I think that you're more likely to see this scenario, number 5 that we're looking at here, I think you're more likely to see this as your initial scenario, the initial question, and that it's going to be advantageous to you sometimes to take that interval from a to b and chop it up into your own two intervals, from a to c, and then from c to b. Why would I ever want to do that? It sounds like I'm making more work for myself. Sometimes you can't get around it. Remember, we saw a problem earlier where our curve went like this, and the area that was inside the first portion of this was positive, and this was negative, and then this area under the curve was positive. If you want to find the area under the curve, but what you would really like is to find that area which in and of itself is negative, and you want to take it and make it positive, essentially reflecting it up over the x-axis, then you're going to have to find the integral from here to here all on its own and then negate it. So if this were an x-coordinate of a, and this were an x-coordinate of b, and this were an x-coordinate of c, and this were an x-coordinate of d, if you integrate from a to d just straight away, then this area is going to get interpreted as being negative. But instead, if you were to integrate your function from a to b, then this would be a positive area. And then, if you integrated from b to c, you would end up getting a negative area. So instead of integrating from b to c, you could integrate from c to b, and that would take this negative area and make it positive also. And then you would integrate finally from c to d, which we know is going to give you a positive area because that curve is above the x-axis. So I did a couple of kind of clever things here, one of which is switching my limits of integration. The c to b became b to c, right? I swapped those so that it would negate my already negative area under the curve and make it positive. And the other clever thing that we did is we used this property number 5 in order to chop up our interval so that we can find the area under the curve in a very specific way, where we're not getting sort of stabbed in the back by that negative area down there, if we don't want it. As I said earlier, sometimes you want it, sometimes you don't. That's a visual representation of chopping up the interval using the A, C, and B values that they used in their articulation. I was using A, B, C, and D because I was referring to a different diagram that we saw earlier. Yeah, these are nice. They're kind of commonsensical. Number 6 says that if your function is greater than 0, in other words, if your function is above the x-axis, then when you find the area under the curve from A to B, then the area under the curve is going to be positive. Yeah, for sure. If I'm finding the area under the curve right here and I'm above the x-axis, the area is going to be positive. If I've got two functions and function f is greater than function g, here's function f, and this is function g, then, excuse me, the area under the curve of our function f is going to be greater than the area under the curve of function g. Yeah, definitely. This area is definitely larger than this area. Told you it was kind of commonsensical, but nice to see some beautiful illustrations to go along with it, right? Number 8 says that if a constant value is less than your function is less than some other constant value on an interval, then I suppose I should tell you that this is equal to, my pen is making weird snapping sounds, I don't like that. This is actually equal to the integral from a to b of lowercase m with respect to x, and the rightmost portion of this is actually equal to the integral from a to b of capital M with respect to x. We saw this previously as a definition, and this is the same thing. This is where it turned out that what you were really doing in the integration process was finding the area of a rectangle. And I drew a beautiful pen-drawn diagram, and then on the next slide they had the pre-printed one. Okay, so knowing that this is really the area of a rectangle, and this is the area of a rectangle, what we're being told in number 8 is that the lowercase m rectangle is literally below the function, and the uppercase m is above the function. Let's draw it. For as bad as my diagrams are, I'm always happy to draw them. Let's have this be lowercase m, it's uppercase m, and let's have this be lowercase m, and we're going to integrate from a to b, and I need another color, purple, yellow. Let's try this one. Let's have this be our function, lowercase f. This is going to really blow you away. You ready for this? The area of this rectangle, the area under the curve from A to B under capital M, that area is greater than this area that's under our curve from A to B. I know, you're floored, right? That's what this says. that the area of the curve is less than the area under the taller rectangle. Should I draw the other one? This over here says that this area under lowercase m, which is a constant value, that area under the m curve, I say air quotes because lowercase m is actually a straight line, that area is less than this area. Okay, that's what this says. That if your rectangle, if lowercase m is below your function, then the area under the thing that's below your function, that area is going to be below or less than the area under your function. We're so thorough in mathematics that sometimes we have to state the painfully obvious. But to some people, those ideas were not as obvious as they are to other people, so that's why I want to make sure to touch on them. If your function is greater than 0, then your integral is going to represent the area of the curve. That's the geometric conservation products. Yeah, if your function is above the x-axis, then your integral, or your area under the curve from a to b, is going to be positive. Well, there's the illustration for property 8 with the capital M and the lowercase m. I like my diagram better. And that is it. All right, how far in are we? 57 minutes. I'm going to stop this video here, and I'm going to do a separate video where I work out some specific problems. And like I said, I was going to talk about some homework problems that I'm going to give to my own students. So stick around. There should be a link somewhere. I don't know if it's there, or if it's there, you should be able to just click and go right into the next video. See you there.